This is the first lecture on Chapter 5 for Calculus 3. In this lecture, I'm going to talk about the type of functions that are studied in Chapter 5 and also the notation that I will use for these functions. So first we'll start by looking at the functions we've studied so far. The first one, of course, are scalar functions. That is a function, which I'm going to call f, that maps either R1, R2, R3, maps them into, I should change color for this, maps them all into R1. So that's a scalar function. The end result of a scalar function is a scalar being just a number. In our case, it's one of the real numbers. The other thing that we've studied so far are vector functions of single variables. These are those parametric equations. So we're talking here about parametric equations. These are vector functions, so here's the bold face. In this case, I'm using R, which is typically what we use for a parametric equation. And for these functions, they're going to take a single variable, usually t, but not always, and map it either into R2 or R3. Here are some hopefully familiar examples of the vector functions as parametric equations that have been studied in the first 4 chapters of this class of Calculus 3. The first one was a function that used vectors to draw out a line in R3. Remember, it started at some point P0, and that would be 2, 4, 5, so that would be the coordinates of the point P0 in R3, and then the other terms, which have the t associated with them, are the vector that goes between P0 and P1. In this case, the 3, the -6, and the 2. So this is the parametric equation of a line that goes between 2 points in R3. And you can see it is a function of a single variable. The variable is called t, and that's, of course, very common. Here's a parametric equation for a circle using sine and cosine. Again, it's mapping R1, denoted by the single variable t, into, in this case, R2 because it's a circle. And then the helix that we studied extensively, mapping R1 into R3. So what's new for this chapter are vector functions of several variables that are parametric equations. There will also be vector functions that create vector fields. So I'm going to start by looking first at these parametric equations. So again, using R for the parametric equation. Now in this case, it's mapping R2 into R3, and the two variables in this case are theta and phi. So instead of just the t, now you have theta and phi, and what ends up being described is a surface, not a line, but a surface. The previous ones with mapping a single variable gave a line. It could be a straight line, a circle, or a helix. Those were the examples, or a more complicated line. In this case, we're going to take two variables and we're going to map out and describe a surface. So here's some examples. Again, these parametric equations give the vector from the origin to the surface. So you can see that right here. You see that little vector r, which you can barely see. Here's another vector r that you can barely see. And that is the parametric equation. That's the r from that vector function of the parametric equation. And its endpoints, as it moves around based on whatever its two variables are, what the values are, it traces out a surface. This traces out sort of the saddle-shaped surface over here, and this one is tracing out a cone. Now this is another function that's sort of a new function that's being studied in this chapter 5, and it's a vector function of several variables, but instead of having its endpoints, instead of being stuck at the origin and just having its endpoints define a surface or describe a surface, this vector function will give a vector, will assign a vector to every point in the domain. Let's just say perhaps through all of the of R3. this is going to create a vector field. Here's an example of a vector field. This is flow around some kind of airfoil. This one right here. The little vectors, the little red vectors that you see here, or the vectors that you see on this sphere, are the vector field. The function gives these vectors. They are located at some point in space, and that's the point where they're defined, and then their direction and magnitude give the, of course, the direction and magnitude of the vector field at that point. So these are two kinds of functions: a parametric vector equation that will describe a surface, and the other is a vector field that gives vector values throughout space. Now there's some notation. I hope that I've been consistent throughout the written lectures and the homework and also these video lectures using a certain set of notation. When you look in Stewart or Thomas, you will see other notations. You just have to fight your way through those. I will try to use a standard notation. The reason for this is that you will not be distracted by trying to figure out what this thing is and be able to focus on the calculus. In this notation, I'm going to use capital F, boldface, for the vector function that gives the vector field. This will map R3 into R3 or R2 into R2. Lowercase r, again a vector because it's in boldface, will describe the parametric equations. In the previous chapter, it was a parametric equation for a curve, and that would be R1 into R3, R1 into R2. For this chapter, it's a parametric equation for a surface, and that will be mapping R2 into R3. Lowercase f, not bold, is a scalar function. Of course, the output of all the scalar functions is a scalar. I'll also use standard notation for the components of the vector field. So here's F being your vector field. You can see it's mapping R3 into R3. And the I component I'm going to call M. The J component I'll call N. And the P component, the K component I'll call P. Okay, some people go M, N, R. But since R is used so many other places in calculus, I'm avoiding the use of the letter R. So M, N, and P are the components of the vector function that gives vector fields. That would be capital boldface F. If it's only in two space, then just M for the I component, N for the J component. For the parametric equations, I use G, H, and K. U and V here are the two variables for the parametric equation for describing surfaces. These could be theta and phi, for example, but just for dummy variables I'll use U and V. And here is your parametric equation describing a curve or a line